To express how much confidence we have in a measurement, scientists use significant figures. These digits tell us which part of a number is reliable and which part is uncertain. By definition, all digits in a measurement, including the estimated final digit, are known as significant figures. Recorded digits in measurements convey both value and certainty. For example, if a length is measured as 12.3 centimeters, the digits 1 and 2 are certain, and the 3 is estimated, giving the measurement 3 significant figures. Similarly, if the volume of liquid in a graduated cylinder is read as 21.8 milliliters, the digits 2 and 1 are certain, and the 8 is estimated, also resulting in 3 significant figures. Now consider two measurements involving zeros, 0.00450 grams and 1,500 grams. Which zeros in these examples add certainty, and which are just placeholders? Now that we understand why significant figures matter, let's learn how to identify them correctly. Every digit in a number has a role, but not all digits are significant. Zeros can either add certainty to a measurement or serve as placeholders, depending on their position. Let's go through the rules step by step. Rule 1. All non-zero digits are significant. The first and simplest rule for counting significant figures is that all non-zero digits are always significant. For example, a mass recorded as 24.1 grams has 3 significant figures, with the digits 2, 4, and 1, all contributing to the measurement's accuracy. Similarly, a substance measured as 3.456 moles contains 4 significant figures, with each non-zero digit, 3, 4, 5, and 6, being significant. Rule 2. Zeros between non-zero digits are significant. Zeros that appear between non-zero digits, often called captive or interior zeros, are always significant because they represent actual measured values rather than placeholders. These zeros indicate the precision of the measurement and the instrument's ability to detect detail. For example, a mass recorded as 1,005 kilograms contains 4 significant figures, with the zeros between the 1 and 5 contributing to the overall precision. Similarly, a volume measured as 8.06 liters has 3 significant figures, with the 0 between 8 and 6 being significant. Rule number 3. Leading zeros. Zeros to the left of the first non-zero digit are not significant. Leading zeros, which are zeros to the left of the first non-zero digit, are not significant because they serve only to locate the decimal point and do not affect the value of the number, not represent any measured information. For example, a length recorded as 0.0025 meters contains 2 significant figures, the digits 2 and 5, while the leading zeros are ignored. Similarly, a time measurement of 0.000507 seconds has 3 significant figures, with the zeros before the 5 not contributing to the measurement's precision. Rule number 4. Trailing zeros. Zeros at the end are significant only if a decimal point is present. For instance, a mass of 8.100 grams has 4 significant figures, and a volume of 0.0100 milliliters has 3 significant figures. In both cases, the zeros after the decimal point indicate that the instrument could reliably measure to that level of detail. Trailing zeros after a decimal point are always significant, as seen in 85.000, which contains 5 significant figures. Trailing zeros before a decimal point and after a non-zero digit are also significant, such as in 190.00, which has 5 significant figures. However, trailing zeros before an implied decimal point can be ambiguous and may merely serve as placeholders. For example, 2,100 meters could have 2, 3, or 4 significant figures depending on context. To eliminate ambiguity, scientists often use scientific notation. 2.1 times 10 to the third power meters clearly has 2 significant figures, while 2.10 times 10 to the third power meters has 3, showing exactly which zeros are significant. Rule number 5. Exact numbers have an infinite number of significant figures. Exact numbers are values that are known perfectly, either through counting or by definition, and they are considered to have an infinite number of significant figures. Because these numbers are exact, they do not introduce uncertainty into calculations. For example, by definition, 1 meter equals 100,000 centimeters, which also has infinite significant figures. When performing calculations, multiplying or dividing by exact numbers does not affect the precision of the result, since these values are inherently certain. Rule number 6. Numbers in scientific notation retain only the significant digits shown in the coefficient. This form eliminates ambiguity by clearly separating precision from scale. For example, 2.20 times 10 to the power of 3 contains 3 significant figures, while 1.0090 times 10 to the power of -2 contains 5 significant figures. Scientific notation ensures that both very large and very small measurements can be reported in a concise and meaningful way, without confusion about which zeros are significant.